autoencoders. What a beautiful topic for today. So here we are. What are autoencoders? How do they work? 2 minutes of theory, and the rest of the video will be coding Python code in TensorFlow2 with our Keras library. Now, at first here we look here and we have here a woman, we have a data input space, and then we have a neural network with some deep layers. And then if we put our information from the input space through the network, we have the task that we want an encoding of our data, of our information, in a lower dimensional space. We call this space a latent space, and you can see here on the y-axis it is much smaller here than the big input space. And what we want to find is how small can I become with the parameters in my latent space that all of the critical information in the input space is still preserved. And if I turn around now from here and I look back, that can I reconstruct my information in the input space if I use here this autoencoder. To construct an autoencoder, we will use a mathematical abstraction called a Keras layer. So here is the first information flow. This is part 1. We go here from our input space. We have here all the different Keras layers with the different hidden units in our layer. And we get a representation in a low-dimensional latent space. Now, then we turn around and we look from this latent space and we want to reconstruct our information in the input space. How is this done? This is the beauty of autoencoders. Now, what we end up with if we do the view backwards, we will have a reconstruction now in the input space from our latent space. That is not perfect. It will have some delta, some difference to the original information when we started to go here, and then when we came back there will be a delta. We can compare those two information, and with the delta you are familiar now. We have back propagation, we go back, forth, back, forth, back, forth. The network learns. You know that the delta should become minimum, and then if you have the latent space at a certain low dimensional configuration, you can be quite sure that the information content in the latent space is equivalent to the information content in the much bigger input space. So we have an encoding, and this is where autoencoder got their names from. Okay, so at first, of course, the question is, how many layers do we need in our network? And also looking at a specific Keras layer, how many hidden units do we need? Some people call, by the way, units a neuron, some other call it cells, whatever you like to call it. How many elements, how many units we need to have in our Keras layer so that we have an optimized configuration space for our model. Let's have a look at this in detail. What are we operating with is an encoded mathematical formalism. We are operating here with tensors in TensorFlow2, and we use with Keras a high-level API of on TensorFlow. So we have TensorFlow.Keras, our API, .layered, we need layers, and then we have .dense. So we need a specific type of layer, and they are pre-programmed for us. We just have to fill in some parameters, but careful. Parameters here will change a lot of if you do not know what to fill in. At first we have units. Now units are the number of hidden units in a layer. 8, 12, 200, whatever you need. Then we have the activation function, a non-linear activation function for the learning in the network. Then for the kernel, we have an initializer that is set already by default. We have a regularizer you can set for your specific task. You have constraints you can set, but I would say let's focus on our code on the first 6 parameters before it gets a little bit too complicated. So remember, what is the mathematical operation we want to achieve with our layer? Our TensorFlow Keras dense layer implements a mathematical operation. Calculates the dot product from two tensors, from our input tensor with our kernel. Then we add some bias, and then we calculate here the activation. Now, activation function, you know, we can have ReLU activation function, we can have leaky ReLU, we can have tangent hyperbolicus, whatever you need for an activation function for your specific task. This is a simple thing to do. However, the dot product is not that simple. Why? Now, activation, clear? The kernel, if you're not familiar with the wording, the kernel is a weights matrix. This is the tensor of our weights created by the layer. And it is interesting, if you do now a TensorFlow.tensor dot operation in a high-dimensional space, it is not easy, because the dot product between the input and the kernel are happening along the last axis of the inputs, you remember, and the axis 0 of the kernel. And the beautiful thing with Keras is you do not have to care about the application of the tensor dot code, where you put your axis, and if you mix up axis or whatever, it is done for you. This is the beauty. So, 2 minutes theory are gone. This is the summary. Autoencoders. Autoencoders are neural networks that learns to compress data while minimizing the reconstruction error. Now, the learning is simply done by minimizing a specific loss function. I will show you in a second. And please remember, although you have here encoder, the autoencoder was invented long before the transformer mechanism was discovered. Autoencoders we had in the 1990s already. So do not mix it up with a transformer encoder, because autoencoders are feed-forward networks with all the beauty of deep autoencoders. And we have two applications right now. We have a dimensionality reduction autoencoder when PCA is not enough. Well, of course, you can say we have UMAP and parametric UMAP with high topological insights, but we'll sometimes use, instead, when the linearity of PCA breaks down, a dimensionality reduction autoencoder. I show you the code. And then, of course, we have a denoising autoencoder. I will show you in my next video. Then we have pictures, and we will put some noise on those pictures, and a denoising autoencoder will get rid of the noise on our pictures. So we have beautiful, clean pictures. And the beauty of a deep autoencoder with at least one additional hidden layer inside the encoder itself is that it can approximate any mapping from input to code arbitrarily well, given that this hidden layer has enough hidden units. So this is it from theory. We have autoencoders, feed-forward network. I show you dimensionality reduction, then denoising, and maybe we will have a look at the variational autoencoder. But let's go now and code in COLAB. And here we are in our COLAB notebook. This is an official COLAB, so you can go along. I have here either you want to have the tutorial from TensorFlow, or here is the link to this COLAB notebook. I will leave a link also in the description, so you can follow along if you want. So at first, all our libraries, what we need: NumPy, Pandas, TensorFlow, everything from Keras. Let's just do this, and then we will load our dataset. Now, we will have the fashion dataset here, so we will have pictures of different things with a resolution 28 pixels times 28 pixels, and we will run here, of course, in grayscale, because we have no RGB, and this is just for the visualization. So let's have a look how the data look like, that you get a feeling with what we are dealing. So this is our pictures. Here the first we have a picture, 28 pixels times 28 pixels of a shoe, then of a t-shirt, some trousers, and here we go. So you see this is our 28 times 28 pixel matrix. That is our input data. Now, our deep autoencoder, and this is what we're gonna construct now here, is here a class model. And we're gonna have here a Keras model subclassing API that we will use, but with the easy sequential model. So as you can see here, we define a class autoencoder, and we have then two Keras models. The first Keras model is TensorFlow Keras sequential model, and here we define the encoder. So we go from the input space to the latent space. And then we have here TensorFlow Keras sequential, the second model, and this is exactly doing the reverse. It goes from our latent space to our original data space with our 28 times 28 pixel. Now, how you can do this? Easy. If you use TensorFlow, it is so easy because everything is done already for you. You have here, you don't even need to define the input space. I just did it to be on the safe side, but you can get rid of this. You're really important. Your first layer is that you flatten your input data. Everything becomes flat. Then you have a dense layer. I have here chosen just by accident 256 hidden units with an activation function ReLU. Then I take a 128 also with ReLU. And then I reach here my inner core, my latent dimension. And this is by definition 64. So we have 64 hidden units in our latent space. And that activation function is, of course, ReLU. I call all of this, this is the TensorFlow model Keras sequential. I call my 3 dense layer encoder. And we do exactly the same in reverse now for the decoder. You have here the decoder. This is a TensorFlow model Keras sequential. I have my dense layer 128, my dense layer 256, and here my output layer with 784. And this activation function here, careful, the last layer of course needs a sigmoid activation function. And then we just do a layer reshape because my 784 I want to have in 28 times 28 so that I can have a picture, a visualization, and I give it the name my 3 dense layer decoder. Now, to the deepness of our encoder. Normally, what you're gonna say is that you have to have the flattened layer, and then a lot of people go directly to the latent dimension layer. Now, I've chosen here to insert those 2 dense layers with 256 and 128 hidden units because I want to have a gradual approach and I want to have the benefit of a hidden feed-forward neural network. You do not absolutely need this for this particular task, but if you have more complex tasks, I do not recommend that you just have a flattened and already the dense layer in the latent space. You have to structure the transition from a 700 or 1000 or 5000 dimensional space to a 10 times dimensional space a little softer. So this is why I go with additional layers. And of course, if you have a symmetric encoder-decoder structure, you do not have to have this, by the way. This is also why this 2 additional layer I put here in. Of course, it would be absolutely okay for the decoder just to go with your output layer and your reshape layer. So this is here to say that you define here your autoencoder model with TensorFlow Keras, the high-level API of TensorFlow2, and then of course we have to do the computation. Now to define this, we have here our call, and we have here the encoder and the decoder of the encoder. This is easy, and then we just call our autoencoder on the latent dimensionality of our latent space. So this should be done in seconds, and remember, a layer here is a mathematical construct in Keras which encapsulates a state with weights and some computation that is defined in the call. Beautiful. Now, as you know it from all the other models, you have now to compile your model. You have to define the optimizer. This is here in Atom. You have to define the metric and you have to define a loss function. I go here just for demonstration purposes with MSE. Please choose accordingly whatever you prefer. We compile our model and then it is time to train our model. You see very easily autoencoder.fit. Now, remember, we have now our xtrain. Xtrain, this is not a mistake because we have this input and we want to have the input back because this is an autoencoder. The number of epochs you can shuffle and a validation data set is a standard procedure. Now, if we go through this, we wait till the epochs have been calculated. You then can have a look at the loss function. Either you do it that you define some checkpoints, or in my case, just for demonstration purposes, I'm just interested in the training loss and in the validation loss of this TensorFlow model. So I just do a matplotlib function, and I just want to see if it develops in the right way that I expect this model when it is trained to be developed. So let's have a look now at the history function with the training loss and the validation loss. Come on. 9 of 30, this takes quite some time. So let's have a look what's coming next. Then there's a beautiful function. If you have now autoencoder, encoder, and autoencoder decoder summary, we have now the possibility to have a look at the structure. Just going back to show you, remember, in our autoencoder, we have here our encoder, so .encoder, and our .decoder. And this is exactly what more or less we now request with this command. We want to see here the summary of this model, and then what we do, and this is the beautiful thing, more or less, why we do this. Then you can say autoencoder encode, and then we take some test data, for example. But this is now only with the encoder. So this means that we have here the low dimensional, or if you want, intense representation of the information of the input space, now transferred in a highly compact latent space. And this is the result. We will encode this in an image and we will have a look at it. And then, of course, as I told you, this is if you look now from the left side to the low dimensional latent space, and then you turn around and you look from the right side, from the latent space, you look back to the input space. Imagine you have a flashlight and you shine at the latent space, and the rays of your flashlight should in some distance project you all the information in the original input space. This is what we do. We say autoencoder decode. And what should it decode? Well, of course, our encoding, our encoded images. So here, finally, the computation has come to a close. As you can see, in blue, we have the training loss, and in orange, we have the validation loss. I think it is not too bad. Just for demonstration purposes, this is what we expect, so the model does not behave any crazy. So let's have a short look at the summary. As you can see here, for my encoder part, for my sequential model, I have here a flattened layer, I have a dense layer with 256 hidden units, then I have another dense one with 128, and then finally I come to my latent space with 64 hidden units. Of course, this is also a Keras layer, and you see that the number of trainable free parameters on the right-hand side. And then I can do the same now if I look back from the latent space to the original information space. We have now the same in reverse. We start here from the latent space with our 64-dimensional core, if you want, and then we blow it up if you want. We project it to a 128-dimensional, 256 and 784-dimensional space, which we then transfer, we reshape, we anti-flatten back to 28 times 28 pixel. And then we have our original pixel size again. And as you can see here, our input, oops, it's not here. Where is it? Our input in the model here, our input shape was 28 pixels times 28 pixel. This was our encoder input. So beautiful. This is how you can check the structure of your decoder, of your encoder. And now let's do this calculation, because this is why we did it. We want to have now the highly if you want encoded information in our latent space, this is here in our encoded images. And then we take this, we shine the flashlight now on our latent space, and we reconstruct with the decoder in the original input space now the decoded images, what the system comes up with after the neural network, the feed-forward and backpropagation. Everything has been finished with the calculation after, I think, 30 epochs. And this is calculated now. Of course, I need a NumPy array for the further visualization. If I want to put it in a picture, I have here a step where I say reshape. My 200, my pixel now is a much smaller pixel size. For my 64 latent space dimensionality, I go now with an 8x8 tensor. So I want to have a two-dimensional visualization. This is the only thing why I do this. So let's do this and have a look at it. And then finally we see here in the top line, we have the original images that I showed you. This is the original images that we loaded as an external data source. And here in the lower row, we have now our decoded. So this is the result that we went from the input space to the latent space and from the latent space back to the original space. And in the original space, this is what our neural network provides us as a result. And if you compare now the input data, the original data, to our calculated decoded data, you see it is not so bad just for the short program that we have. Here for the t-shirt, I think this is Lee t-shirt, you see that here the structure is still missing, but of course we just did a very small demonstration network. And here you can see I have it here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For 10 pictures you can see how well your model performs. I like to have a visual verification of the performance of my model. Just if you have figures, it doesn't tell anything. I would like a visual verification always, and I can recommend this to you. Now, if you say, okay, so this is the decoder, this is the full part from left to right and from right to left from our encoder structure. But here we just have now from the input space encoded in our low dimensional latent space. This is what we call encoded images. Let's have a look at these encoded images. And here are our encoded images. How do they look like? And as you can see, hey, wow, this is the structure, how they look like. Let's go a little bit closer. So the first one here, this shoe or whatever it should be, is now here in a highly, let's say, compressed low dimensional representation. We have 8x8. This means 64 pixels instead of 784 pixels. We have now more or less the same information content encoded in this pattern, that if we shine our flashlight on this latent space, we can reconstruct here this decoded picture, and it gives us this particular shoe. And if you train this, and if you do more and more training, you can get better and better, of course. So now a lot of people ask, hey, why isn't it a shoe if you have just 8x8 pixels? Now imagine if you look here, if you have here this picture and you see here, for example, in the upper left corner, there's so much black, and this information space is black. This means it holds no valuable information. Now, if we have hundreds and thousands of pixels and the object is somewhere in the middle, I can afford to have a black background where there's no structural information on the object in the picture. But if I only have like here 8 pixels and 8 pixels, so I have to use all the information space to encode information that when I shine my flashlight on this pattern, at the end, in some meters distance, I will see finally again here my decoded shoe. And so this filter, this encoded filter, this low dimensional latent space representation, this embedding, however you want to call it, it has to use every pixel. So you will not see here the shape of a shoe, because we would lose here the information space, and this is 8 and this is 8, we would lose here about 25% just missing that we do not use for encoding the information. Therefore, you can see here every single pixel has a specific value, and you will not have in the low dimensional encoding now the picture of a shoe, but this is here a highly dense mathematical representation of the autoencoder. And this is the beauty, because this picture here has now the equivalent of all information for this particular picture of a shoe with this particular model. And if you have, for example, not a shoe here as a starting point, but you have a word embedding with 700 dimensions. So there's a word, and then we have 700 parameters on the right side. There's another word, and then another 700 parameters, and we have 10,000 words with each 700 parameters. And you want to bring it down to, I don't know, 25 dimension, 25 parameters for each word. This is exactly where we use here our autoencoding. And this is where this beautiful structure, and again, I'll show you the model. This is it. Is so beautiful. It does all the work for us. And in Keras, the beautiful thing is with the subclassing API, you just define your encoder, you just define here with single lines your decoder, and we are not even here in the professional functional interface. We're here working with a sequential model, so this is the simple model, parenthesis, and you just define here input, flatten your different layers. You do not have to define that the output here is here the input. Model Keras does everything for you. You do not have to care about this. You do not have to care about the tensor dot mathematical calculations that are going on in the background. Keras is taking care about all of this for you. So this is, even for a beginner, a beautiful, beautiful way. TensorFlow2 with high-level API Keras to do an autoencoder. Beautiful. So the first, the dimensionality representation I showed you. And the next video will be about, and you already guessed it, image denoising. So we will get rid of the noise in our pictures, and you will guess it, we will do this with an autoencoder. There is, of course, everything ready for you, and I see you in the next video.